So I want to talk about C APIs today in Swift, because I think it's really, really exciting. So those of you that know me might know that I'm really excited about Swift, and mostly about the fact that we can do functional programming. I think functional programming is really cool and allows for a lot of awesome stuff, but there are more things about Swift that I think are really, really cool. And one of them is the way it interoperates with other languages, like Objective-C, which is very natural, and like C, where they also did a really great job. And I'm writing another book about Swift, Advanced Swift, which will be out soon somewhere. And we started this before Apple announced Swift 2. And specifically, we started this before they announced that Swift would be open sourced. And I think this it's going to be a huge thing. And it's been also a very big influence for the book, because now we focused in the book a lot more on C Interop, because I think this is going to be very important. Once we have Swift on Linux or on Android or wherever, we need to work with existing libraries. And a lot of these libraries are written in C. So it's going to be very important that we can work with C libraries and that we can do nice things there. So that's why we focused more on this in the book now, and we added another chapter, and that's also what I'm going to talk about today. And I'm going to show a very simple example, but we're going to make it nice and complicated so that we can see like sort of what kind of things you can do. So let's get started. I don't have any slides once more, so we're going to do live coding. And as always, this might go wrong, so please help me. I've also built in a couple of mistakes on purpose, so I'll tell you when I'm lost, and then maybe you can help me. So this works, the hello world. That's very simple. And what I want to do is I want to wrap qsort, and I want to make a Swift wrapper around it. Swift already has very good sorting built into the language, so we don't need to do this. It's just a very good example to show why and how we could do this. So we can just start by typing qsort. I'll delete this. And then we get this big auto-completion. And if I press enter, there's not much we can do with this. So the way to learn about how these functions work is with C, with the manual. So you can type man qsort and press enter, make it a little bit bigger. And then you get this huge manual page. And here are the qsort functions. So let's look at this type, qsorts, parameter by parameter. Or let's just start reading from the very start. So the first thing to notice is that it's defined as void qsort. This means that there's no return value. It returns void, which is interesting, because it doesn't really return a new sorted array. It's going to sort the array that we pass into in place. So this is something to realize. It's an in-place sorting algorithm. Then the first parameter is a void pointer to base. And this is the C way of saying this could be a pointer to anything. In our case, it's going to be the pointer to the first element of the array. And because C doesn't really know what kind of array we have, we might be sorting integers or strings or whatever. That's why we have to type void there. We need to cast this. So this is a pointer to the first element. Then the next two parameters are a little bit simpler. The number of elements is the second parameter. That's easy, that's just an array count. And then the third parameter is the width. And this is the number of bytes in memory. And this is also very tricky. It's actually easy to do right, but you just need to know how to do this. We'll look at this, how to calculate this. And then the last one is the most interesting one. This is a comparison function. This is also the hardest to read. So this is a function pointer called compare. And the function pointer needs to return an integer. That's why it says int star compare. And then it takes two arguments, a constant void pointer and another constant void pointer. And these will be pointers to the elements of the array. So this function will compare two elements of an array. And the reason it's void because we don't really know what kind of array, and it's const void because we don't want to mutate the array. That's what the sort function is doing for us. We don't want to do it in this function callback. This might sound complicated, but we'll see how it gets imported and how we can work with it. So let's try to use this. Back to Xcode. So we can see that this void pointer gets imported as an unsafe mutable pointer void. So this needs to be a pointer to the first element of the array. And now the question is, how do we take a Swift array and create a pointer out of that? So the first thing is, of course, to create an array. So let's make an array numbers. And then we're going to put some numbers in there, like 42 and 7 and 3 and maybe 4. This is the array that we want to sort. And the way we can make a pointer out of something in Swift is just by using ampersand, just like C. And now we will have a pointer. This is not completely right, but we'll see why. The second step that we need to, or the second parameter that we need to pass in is the number of elements. So this is very easy. We can just say numbers.count. And then the third parameter is the size of a single element in memory. So if you're used to C, you might think it's size of int. This is how you would do it if you were programming in C. And this is almost correct, and it will work in most cases. However, what we need to do is we need to use stridov. And stridov is the real size in memory. So stridov. The size of an integer is the number of bytes it occupies, but the stridov also accounts for the platform. So on different platforms, there might be different padding added to your numbers to make sure they align all right. So we always need to use stridov. That's basically the thing to remember. And then we need to write a function pointer. So how to do that? We can copy this type. Let's see. Sorry. Let's try to copy it and make a function pointer like that. Let's call it compare. So I'll paste it back in, and we can make a function compare. So it takes an unsafe pointer, another unsafe pointer, it returns an int32. So this needs to be a brace. So for now, let's just return 0. We need to name these parameters, so let's call them left and right. And now we're almost done, and we can almost run it. It's not comparing anything. So this is a very interesting error message. If we open this up, I'll zoom in a little bit. It says, cannot pass an immutable value as in-out argument. Numbers is a let constant. And because quicksort is sorting in place, Swift is not going to let us put a let in. It wants to put a var in, because a let can never change, a let array. We need to make a var array. So Xcode is nice enough and says fix it. So I can just press enter. And if I zoom out, now you can see that numbers is a variable instead of a let. And now at least the compiler seems happy. So we can try to run it and nothing will happen. It sorted the numbers maybe, but we need to print them as well. And now hopefully we get at least the numbers out, unsorted. So that's the first step. We were able to successfully call a quicksort function, and we passed the array in, and it didn't segfault. So that's already a huge accomplishment, I would say. So let's try to implement the compare function. So as I said, it gets two parameters, two unsafe pointers to void. And we need to cast these two pointers to integers. We know that we will pass in integers into this function. So we need to cast this ourselves. And the way we can do that is, for example, like this. There's a couple of different ways. So we could say let left equals an unsafe pointer of integer, and then put this L in. And now it will complain that we didn't use left, but this is one way to do it. A nicer way, which I prefer, is to say left is going to be an unsafe pointer to integer, and then not specify this type here. And now the Swift type inferencer will infer it for us. And we can do the same for right. This is almost the same code. We say unsafe pointer, and we put the R in, and now we can compare the memory of these pointers. So we can, for example, say if left.memory and you can see that the auto-completion says this is an integer, so this is the real element. This is the real integer that we're comparing. So if the left.memory is smaller than the right.memory, we return -1. If the left.memory is equal, then we return 0. And otherwise, we return 1. So let's run this, and then we can clean it up a little bit. But first, make sure it works. And we have a sorted array. Yeah, that's a good first step. So this is a lot of work to sort an array, right? What we can also do is we type this left.memory all the time. We can just do this straight away. We can say left is going to be an integer. We can delete this. And then here just say .memory. Do the same for right. It's going to be an integer. And move this .memory out. And then the code will be a little bit simpler. So hopefully it still runs. Cool. So now how to compare strings. You would write almost the same code. Before we do that, I want to make like a small abstractions. I'm a functional programmer. I like abstractions. So I want to put all this stuff into its own function. So what I want to do is I want to write a function, qsort, which takes an array of integers, and it returns an array of integers. And then I'm just going to move this qsort line in the function, and we need to rename this, of course. So this is now called input, input.count. We can leave the compare, and then we return the input. So now we have it into a function, and we can say qsort numbers. Right, it's exactly the same error. The cool thing about Swift is that all the parameters are automatically defined as let. And there are two ways around this. We could either make a copy inside the body, saying something like this. And then we can use that copy, or we can do what Xcode suggests us. Let's see. And it's going to make a var out of this. And this automatically makes a copy. So now we can run it. And it still succeeds. Cool. So let's do the same thing for strings. Well, I know how to do this. Just copy paste. It's my favorite programming technique. We're going to take an array of strings, and we're going to output an array of strings. And I'm not going to change anything else yet. So now we can make some strings. Like this maybe. And then ABC and DEF. And now instead of sorting numbers, I want to sort the strings. It compiles and it crashes. And this is the big danger of working with C. You need to be very careful that you're doing everything right. Because if you make a tiny mistake while you're wrapping your C function, you could end up with crashing code. And some of the crashes immediately show, like here, and other ones take a while to appear. Like you might not even notice that you wrote the wrong code. At least I don't a lot of the times. So the fix is easy. We can just change this int, which we forgot to change, to string. And now hopefully it succeeds. So it compiled, it ran, but it didn't really sort, or at least it sorted in a very strange way. And this is exactly the same problem, because what we did is in our qsort, we used the compare function. And the compare function, the implementation, takes these pointers and casts them into integers, and then tries to compare these strings as integers. So that's why at least it compiled and it ran, but it just gave back nonsense. So we need to write another compare function. So let's call this one compare int. And we're just going to copy paste it. It's nice, right? All this copy pasting. and say, call this one compare string. And now there are very little things we need to change. We change this to string. And then in the implementations, of course, now we need to use the right ones, compare int for integers and compare string for strings. So now it's sorted. And this is just very simple string sorting. First, all the uppercase strings, and then alphabetically. So it's not very nice sorting, but at least it works. I don't really like how we needed to, copy paste all this and make it like implemented once for every type. And I would really like to make this generic. And from here on, it will get a little bit complicated, but bear with me. So what I would really like to write is something like this. A quicksort function that for any a takes an input of a, and then it returns a sorted array. I think this would be really cool. So we can try, just copy paste this. And now we need to change the stride off, we know that, and we need to write something like compare a. So how to do that? I'll remove the old code, the old quicksorts. We don't need them anymore. And I'll remove the compare string. And now I want to rewrite this into a compare a. So this is a compare a for any a. And now we need to cast this integer to an a. And we can try to run it. And we get a lot of errors. So it says generic parameter is not used in function. And the other problem is that you can only use these comparison operators when you actually have something that's comparable. So it would be something more like this. Comparable. So this is a problem. Another thing that we could do is instead of having a function, we could try it as a closure. This is a bit weirder, but this also should work. And do something like this. And paste this in. So normally with C function pointers, you can do something like this. And this is going to be even more interesting. Now it's the same error. We need to make a comparable. And now all highlighting goes away. So let's try to run this. And this is very interesting. No errors here. Highlighting comes back a little bit. And we get a segmentation fault. So this is it crashes the compiler. So are we doing something terribly wrong here? Why is this the case? And it's actually, we are doing something wrong. The thing is that C function pointers, they cannot take any kind of context. And in this case, we're sort of using this A as sort of context for this function pointer, because anytime we call this function, it's for a different A. And we don't know this statically. We're going to try one more thing, and then I'll show how to fix this. So one more thing that might work, and otherwise at least it will come in handy later, is to do something like this. We can write an extension on comparable. So here we can say, well, for any comparable, I just want this static function there that's going to take the static function called compare, and it's going to take an unsafe pointer of void and another unsafe pointer of void, and it's going to return an int 32, just like the signature we had before. And then let's move this in there. Now, instead of A, we have to name it self. And now maybe we can try this, remove this closure again, and say a.compare, because it has exactly the right type. And that's the same problem. And here we get a little bit more detailed information. It says a C function pointer can only be formed from a reference to a func or a literal closure. Well, we had a literal closure, and we also tried the func, but the problem is that the type was, like, even though here the type was unsafe pointer void to unsafe pointer void to int32, it wasn't really correct. There was also this generic parameter which was sort of hidden in the type, which we didn't have to write down, but this is the big problem. C function pointers cannot take any context and not take any extra context. And this is never going to work with the qsort function. So basically we have to give up. However, if we go back to the manual, we can see two more variants, qsort B and qsort R. Because C programmers also have this problem. They want to specialize this comparison function, but it doesn't really work with the normal qsort. So let's look at qsort B and go over the type. It's almost exactly the same. It takes a void pointer to base, it takes a number of elements, it takes a width, and it takes a comparison function. The only small difference is that this is a caret and this is a star. And the caret means Objective C, means blocks, sorry, it means blocks. And blocks can take context. So we can try to use the qsort B variant and use a block instead of a function pointer. And hopefully that works. So let's run this. Build succeeded. It's sorted. Let's see if it still sorts the numbers as well. And if it works, we're basically done. So it still works. And this is how you can solve it. So instead of using C function pointers, which are very limited and cannot capture any context, for example, generics or things outside of the function, if there's a block-based variant available, use that. However, many of the C libraries that you will work with, if you work with them, will not have a block-based variant available. This is very uncommon. This is like the block-based things Apple provides them normally, but most C libraries don't. So if you have a block-based API, use it and you're done. If you don't, and that's what we're going to do now, we're going to take the hard way and do it without the block-based variant, and we're going to use the qsort R. So let's go back to the manual page. Oh, I closed it. And scroll down. Okay, qsort R. Let's go over the types again. So first there's a base pointer, there's the number of elements, there's the width, and then there's all of a sudden this extra parameter, a thunk. And it's a void pointer. And this means that we can basically put a pointer to anything in there, anything we want. And this is where we're going to put in our comparison function. And then also the comparison looks a little bit different. So it doesn't just have the const void and the const void, but it also has another void pointer. And this is the thing that we put in the first place. So this is what we're going to use to fix our problem, hopefully. So we're going to put a comparison function in there and then cast it, and then hopefully it'll all magically connect back together again. Let's do this. So let's delete this line or comment it out and say qsort R. So the first thing is simple. We put in the inputs with the input count, the stride of A, and then we can put anything we want in here. And if we try to put the compare function, a.compare, it'll complain because the type that C wanted is an unsafe mutable pointer. And the a.compare is not really mutable. It's a static function on a category. It's an extension. It's not very mutable. So we need to make a mutable copy. So we just can make a new variable saying, calling it thunk, and we assign a.compare to that. And then we can put in the thunk. So we need to make sure that it's a variable. And then we need to write this comparison function. So I'll cut the type signature out, call it CMP, and let's write that. So this in needs to be curly brace. So this is going to be our thunk. And it comes in as an unsafe mutable pointer to void. And this is going to be the left thing to compare and the right one, the elements. And now what we need to do is sort of cast this thunk back into the a.compare type. So cast the type back. So what was the type again? I'll just copy and paste this type and make a type alias. So the type alias for the comparison function, this is the type that we want and that we put in. So we can also just add it here just so we are completely sure that we're passing the right thing in and that we take the right thing out again. So here we can say, well, our comparison function is just an unsafe pointer of the thunk and then get the memory out. If we forget this unsafe pointer, if we just write this, thunk.memory, then the type doesn't match because the thunk has type void. It's an unsafe mutable pointer to void. So we need to explicitly cast this. We need to say unsafe pointer thunk. So this is how you can get it out again. And now this is just a regular function again. So we can just say compare left, right, and return that. So there's one more error. It wants us to name the parameter. And hopefully, if we run this, everything works again. So the numbers are still sorted. And let's sort some strings. This also succeeds. So everything is still working. And we made it very generic without using blocks. And this is the same kind of technique you will see over and over in a lot of C APIs. In a lot of APIs, you can pass in some context, and you can basically pass in whatever you want. It'll be of type unsafe mutable pointer to void. And then you need to pass it in and cast it back. And anytime you do these casting things, you need to be very careful. As we saw with the strings and the integers, you might be accidentally comparing strings as integers and stuff like that, and Swift will not help you. It will just crash. So you need to be very, very careful. So just to wrap it up, this is nice. I want to make it a little bit more Swift-like. That's the easy part now. And then we can do questions. So what I think would be cool is to define this as an extension on array. So what I would like to say is something like, well, for every array where the element is comparable, I want to have a function quicksort in place. I'm just going to cut this out. Call it quicksort in place. We don't need this generic parameter anymore. We don't need this input anymore. We don't need the output anymore because we're doing it in place. And now we can just pass in self. Again, normally, so array is a struct and you cannot really modify structs. So wait, before I continue my sentence, you cannot really modify structs. So what we need to do, if we compile this, we'll get an error. Let's try to have element. And it's the same kind of thing. It doesn't allow you to pass an immutable array, and by default, arrays are immutable. So here we can just write mutating. And now, interesting. Right, now this doesn't exist anymore. So what we can do is we can say strings.quicksort in place and print it, strings. Right, and now we need to make it mutating. So only a variable we can mutate. And this is a little bit more Swift-like. This is also how the Swift sorting things work. They say sort in place. The last function, and then we're done, is just a regular non-in-place sort. So let's say qsort. And this is going to return a new array. And what we can do here is something like this. We can say copy equals self. Then say copy qsort in place. And return that. And this is a Swift way to do it. So let's see if it's happy when I build. Right? I didn't run it yet. So now what we can say is strings.qsort. We can print this. And then print the normal strings afterwards. So if we did it right, this means that it will first print the sorted array, but it didn't really change the strings that were underlying it. Printed a copy. So we can here see that it first prints a sorted array and then it prints the original array. So this is an easy way. You can do it both ways around. You can first define an in-place version of your algorithm and then also make a normal version or the other way around. Cool. So I hope that you now have a little bit of an overview of what it's like to work with C APIs. Like I said, you have to be very careful. I made a lot of mistakes when testing this out, and it's nice if you make a mistake and the compiler catches it. It's really horrible if you make a mistake and you only find out at runtime, or worse, in production. And I'm very happy to take any questions related to this or to Swift in general. Thanks. Yes.
So am I getting it right that in first version strings was let and you were using qsort with a block variant? So Swift was thinking that it's an immutable array, but we were modifying it in place behind Swift.
I'm not sure if I completely understand.
So it was a let, right? So in Swift we're thinking that it's immutable.
Yes.
But we were modifying it in place, right?
No. Do you mean? No. So this is the really cool thing. If I let's say if we make a new function test and we put an array of strings in there, because this is sort of how we define it, right? With var. This means that the moment you write var, a copy is made. It's a little bit more complicated. Sorry, I was too quick. The moment you write var, a copy is made, but not really. Only once you start changing it. So it's very efficient. It's sort of like how it works with NSArray. If you have a normal NSArray in Objective-C and you say NSArray copy, then it doesn't really copy it.
So it's copy on write, right?
Exactly, it's copy on write. So, and this is also, it's a very subtle thing, but it's very important to how Swift works. And it took me a while to understand how this works. But anytime you're using a struct, it's sort of expected that it's copying automatically. And you can also implement your own copy on write. So it's not too hard to re-implement Swift arrays using, for example, C pointers or your own allocation. Mike Ash has a really good blog post on this, how to do that.
Thanks.
Any more questions? Yes?
You've created a function, a helper function up there,
Mm-hmm.
and could you also use it now as a closure to qsort?
You mean this one? Or the CMP?
Yeah.
This one? Yeah, let's try it. Because in theory, yes. I asked the Swift compiler engineers, should this work? And they say yes. So yeah, you're completely right. This should just work. So I'll just cut it from here. delete this and put it here. And now we need to say thunk lr in. Build failed. And if we go here, we can see that we get a segfault. There's a warning, but then the rest is segfault. This is exactly the same. Semantically, it's exactly the same, but the compiler cannot figure it out. And I reported this a few betas ago, but it doesn't work. And it's really painful because you like what I experienced. Now I just wrote it down in half an hour, but it took me days and days of figuring this out, and I thought I was doing maybe something wrong inside the function, and it can be a very frustrating experience to do this. But yeah, unfortunately, sometimes you have to just pull it out like this into separate functions, and then everything works again. I also tried adding the types manually. That's something you might sometimes want to try with closures, but that doesn't help either. So there is no way around this. This is unfortunately the simplest way to write it. Very good question, yeah. Any more questions? Yes?
Do you use Swift as your main scripting language?
Yeah, actually.
What do you think about it? Because I have had trouble with some bash function like ls and need to wrap it.
Yeah, well, maybe the nature of my scripts is maybe a little bit different. So what do I use it for? So I have one script. So I'm writing this book about Swift, and then the book is written in Markdown, and all the diagrams are in PDF. And then for what we need to do is take this Markdown and make LaTeX out of it and transform the Markdown and stuff. And we all do this using Swift, using a simple tool. And the diagrams we need to convert from PDF into PNGs for the EPUB variant, otherwise it doesn't work. And this is also written in Swift. But it's very simple tools that just take one file in and one file out, or they take standard in and standard out. And yeah, if you want to do like ls, you need to use the file system APIs, which are a lot more work than using bash. Is there any specific kind of tool you would like to write?
No, I think I need to change from Ruby, for example. So I know there's a lot of probably some basic stuff maybe in the future will be open.
There is another issue with when you're using Swift, and with Ruby you have of course Ruby gems, and with Swift I guess the only alternative is CocoaPods or Carthage. And if you want to use CocoaPods, you can use CocoaPods Roam, and this will allow you to, I can maybe show this a little bit. So here you can, if you have a pod file, you can say use frameworks for Swift, and then you use this plugin CocoaPods Roam, and then you can do something like this. Pod install -- no integrate. And this, if you run this, you'll get this directory pods, and inside there the frameworks are built for you. And then you can, in your Swift file, you can at the top have this hashbang and say -f roam, and then it'll pick up any frameworks in there. So that's how I can use the Common Mark framework and the Literate Swift framework. And it took me a while to figure this out, but then once I had it working, it's actually really easy. And yeah, here you can see that this just is a very simple thing. Like if you don't provide it with 2 arguments, it'll just crash hard and stuff like that. But I found that it works really well. And once you have like a little bit of experience with the painful points, then you can just write Swift and use all your Cocoa APIs. And especially that is a really big advantage. Like when you can just use Core Image or Quartz or whatever, that's very convenient.